our last video in this group, we're going to talk about the length of a polar curve and how to determine that. So if we have r as a polar function of theta, and we know that the derivative r prime, or dr d theta, is continuous on the interval that we're considering, theta between some alpha and beta value, then we can say that arc length is the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. And if you remember, our previous arc length formula when we learned this earlier in the semester was a to b of 1 plus dy dx squared dx. Okay, so very similar formula, just a little bit different. Let's apply it now to an example. So let's find the length of the curve r equals 1 minus cosine theta. And this is going to be the length of that entire cardioid curve region. So in order to use our formula, we need our derivative first. dr d theta, the derivative of 1 is 0. The derivative of cosine is negative sine, so we end up with a positive sine theta here. Using our formula, the arc length is 0 to 2 pi. My cardioid is 1 minus cosine theta, quantity squared, plus sine theta squared, my derivative squared, d theta. So we need to simplify what's under that radical. Foiling my first part, I end up with 1 minus 2 cosine theta plus cosine squared theta, and then I have plus sine squared theta. And we should right away recognize that cosine squared plus sine squared, that is Pythagorean identity, that's equal to 1. So this becomes the integral from 0 to 2 pi of the square root, 1 plus 1 is 2 minus 2, cosine theta d theta. So I see I can factor a 2 out. It's the integral from 0 to 2 pi. I've got the square root 2 times 1 minus cosine theta d theta. And square root of 2 is just a constant multiple in this situation. So this is the square root of 2, the integral from 0 to 2 pi of the square root 1 minus cosine theta d theta. So now we need to deal with this messy integrand. We've got a square root and some trig functions in there. And what we can do is get creative using our double angle identities. So I'm going to come over here and say, well, I know that sine squared theta is 1/2 1 minus cosine of 2 theta. So I could multiply by 2 on both sides. 2 sine squared theta is 1 minus cosine of 2 theta. Now if I took cosine of 2 theta and let that be equal to 1 theta, my regular theta would now be equal to half a theta. So this is 2 sine squared theta over 2 equals 1 minus cosine theta. So now I have the square root of 2, the integral from 0 to 2 pi, of under my radical 2 sine squared theta over 2 d theta. Now, square root of 2, that can come out in front. Square root of 2 times square root of 2 is 2. Got the integral from 0 to 2 pi. And then I'm dealing with just the square root of sine squared. And those cancel. So I have the integral of sine of theta over 2 d theta. Now remember, when we are integrating sine of theta over 2, that's the same as writing sine of 1/2 theta. So that's a coefficient we're going to need to divide by that 1/2 value. So this becomes 2, and I have the integral of sine is negative cosine theta over 2 divided by 1/2 from 2 pi to 0. So this is negative 4 cosine of theta over 2 evaluated from 2 pi to 0. So I have negative 4. If I plug in 2 pi, I've got cosine of 2 pi over 2. 2 pi over 2 simplifies to just pi minus the cosine of 0. 0 over 2. Right, so plugging that 0 in here, we get 0 over 2, which is just cosine of 0. So I have negative 4, cosine of pi is negative 1, minus cosine of 0 is positive 1. So I have negative 4 times negative 2, or positive 8. And that represents the length of this cardioid curve from 0 to 2 pi, that one full revolution. You could think of it as perimeter. And so that's how you can find the length of a polar curve.